Thank you very much, Sasha. It's a pleasure to talk to you about supernova and neutron-star mergers in the turbulence. And while some of you have been speculating that indeed the reason that I'm talking today is that my name is also Philip, it's actually just that I have travel constraint and can't make it on Friday, the multi-messenger day. But either way, we're going to make a pretty hard shift from galaxy and cluster scales to the scales of turbulence inside the engines of transient events like supernova and neutron-star mergers. So we're going from the very large to the very small. Generally, all the things I'm interested in is everything that can explode in the sky. This can be binary black holes, but today I'm really going to focus on, this is the wrong remote. Today I'm going to focus on extreme core collapse supernova and binary neutron star mergers, and particularly how MHD turbulence can play a role in driving these explosions and the outflows and kilonova and short GRBs from these transient events. If I want you to take one thing away from this talk, is really to focus on what we are doing and which challenges remain in turbulent evolution of signatures, and by that, hopefully at some point being able to constrain the turbulent nature of these engines via the observations that we have and that we're getting in much more wealth in the coming years and decades. So which engines are we talking about? So I'm mainly focused on supernova, and specifically supernova that are more extreme than the garden variety core collapse supernovas. So these are superluminous supernova, hyperenergetic or type 1c broadline supernova. Some of these are connected to long gamma ray bursts, but then also short GRBs, kilonova from neutron star mergers, and how all of this ties into potentially also creating the engines and the sources of fast radio bursts. So the question really is there a common engine driving these? Are these just source parameters and the environments that these form in that determine the different outcomes, or is this different engines that play in driving these events? If we want to study this, and just to set the stage for some of the simulations that I'm showing you, quick overview, we need MHD to handle the gas and plasma dynamics. In this particular scenario, we also need gravity and general relativity to handle the relativistic collision, for example, of a neutron star merger. We also need nuclear and neutrino physics, since we're dealing with extremely dense and extremely hot material. We need the interactions of this nuclear material with the neutrinos that are emitted in the cooling of these extremely hot objects. So this is complicated, even doing this without worrying about the turbulence scales that we need to resolve. This is all for forces fundamentally fully coupled. But we also need to deal with fluid and MHD instabilities, multi-D structures. So this is really only something that ab initio we've been able to do in the last couple of years, where we've reached the fidelity and the maturity to even do this in 3D with global simulations. The tool that I'm using is part of the Einstein toolkit. We've recently developed a new GPU driver for that called GramX. This is something that is open source that you can check out if you're interested in studying some of these running tutorials or having students start up with doing relativistic astro. So the first science case I want to look at is extreme core collapse supernova, and specifically hyperenergetic or type 1c broadline supernova. And what this looks like, and we're looking at a volume rendering of entropy. We're zoomed in on the interior of the star. So this is 2,000 kilometers top to bottom. Anything that's red and yellow means high entropy material. Green and blue means cold material. The remainder of the star is still collapsing from the outside. We're just kind of not visualizing it to actually let you see what's happening in the center. And as the star and the iron core collapse, we have a protoneutron star formed that ultimately drives some shock wave out. And in this case, the star is rotating rapidly around the vertical axis and ultimately is driving MHD-powered outflows of high entropy material along the rotational axis. You also see the time here at the top. So this is really just focused on the detailed evolution of the engine in the immediate aftermath of the collapse. And the reason why we can't do this for much longer is because even doing these simulations takes 10,000 CPUs for 1 to 2 months on big supercomputers. So what people typically do in creating the magnetic fields that go into these simulations is just hand wave that the MRI and dynamo action can create these, artificially impose a colloidal field that we would think would result from that, and then study the explosions that remain. But we can also go in and actually study the turbulent dynamics of the shear layer that is surrounding the proto-neutron star. So what we're looking at here is an equatorial cut through the innermost region. We see the proto-neutron star that has just formed, and we're looking at the stability criterion for the magnetorotation instability. So anything in light blue and dark blue is basically unstable, and this is exactly the differential rotation shear layer that is surrounding this proto-neutron star. So one can go ahead and actually simulate that, and people have done that, of course, in shearing boxes and idealized situations, but we wanted to do it in a global simulation that we seeded from a full, consistent iron core collapse, and then study the magnetic field evolution. We've done this here for a couple of different resolutions. So really only the resolutions here on the right, the 150 meter, resolve the magnetorotational instability. And we're rendering the toroidal field. Anything in yellow and blue is magnetized strength field, which is kind of what we require to drive these explosions that I've shown you in the previous simulation. So unsurprisingly, as you start resolving this instability, the evolution becomes much more turbulent. But what also happens is that you see a collection and ordering of this small-scale field created by the MRI into a large-scale structure. And just showing you the high-resolution simulation, you can see this more clearly, where we have these patches of yellow and blue field. These are basically the channels formed by the MRI on a length scale of roughly 1 kilometer. And then as time goes on, these get organized into a large-scale toroidal field on the order of the radius of the proto-neutron star, which is kind of this surface here sitting in the center. And this is essentially what the field structure looks like when people assume a colloidal field would deliver this kind of toroidal field we are just winding. So this is kind of proof of principle that if we do simulate the physics that we think are relevant here, we do get the field that can explain these MHD-powered explosions. If we look at this in a little bit more detail, and this is just the energy spectra of the turbulent kinetic and the magnetic energy, and you see here the different colored lines at different times in the evolution. So we start from this dashed line, and then as first the small scale, so large K saturates very quickly after a millisecond or two. The spin period of the proto-neutron star here is in milliseconds, so that's the driving time scale. But then a bump at K equals 4 grows, and this is exactly the scale of this shear layer around the proto-neutron star. So this is kind of our large-scale amplification that is happening here. We can also look at this at the different modes as a function of time, and we clearly see energy inverse cascade to large scales. This simulation was limited to 10 spin periods of the proto-neutron star, just because this already was 10 billion grid points, and it took us essentially a full, what is equivalent to an inside allocation nowadays. And we were not able to go beyond what we have been doing here, where we showed that we create the toroidal field, we see signs of a large-scale dynamo, but to fully close this and follow, conversion of toroidal into poloidal field, we would need much, much longer times to assess, which also would mean much, much further away boundaries for the simulation setup to not have boundary effects kind of impact our dynamics in the center. So this was something that wasn't feasible to go immediately beyond. What does this imply? So this means that if we have rapid rotation, we get the magnetic field for free, meaning one constraint of like what the engines of these explosions could be is removed, or we get it automatically. But the other thing is that means millisecond period for the protomagnetar that we have in this setup implies rapidly rotating cores of massive stars, and we know this is likely not going to be the majority of stars. So for example, this channel would not be enough to explain the galactic magnetar population. So if we after that we need additional things, what could this be? This could be that we start from highly magnetized cores of massive stars. It could be that the rotation rate requirement that we had kind of thought about here would be not as strict. But more importantly, it could also be other dynamo mechanisms. So this is work from Raynaud in 2020, where they've really looked at the proto-neutron star convection, doing similar things and developing magnetized strength field in the absence of this rapid rotation. So this is something where I think these kind of different global simulations coming together slowly allows us to build a picture of, how does this all map together and which particular scenarios do we need to investigate in more detail. Switching gear now for the second half of the talk, I'm going to look at some of the same lessons applied, but in binary neutron-star mergers. GW 170817 has really demonstrated the massive potential in multi-messenger astronomy via the short gamma ray burst counterpart, but also particularly the blue and red kilonova. But many open questions still remain. In particular, many of these questions connect to the physics of the remnant, the merger, field amplification, and how all of that ties together with turbulence and angular momentum transport. And for example, which engine do we form? Is it a black hole or a magnetar that's driving the short GRB? How does the 2-second delay between the short GRB and the gravitational wave trigger, is that tied to a detail in the engine formation? Is that just how the short GRB emission is made? All of these questions are unclear. Similarly, what kind of remnant do we leave behind? I'm going to go into this in a second in a little bit more detail, but like angular momentum transport mediated via turbulence is key there to determine, does a neutron star collapse? On what timescale does it collapse? How long can it survive? So this is the neutron star merger simulation from David Rodice. You see the rest mass, gas density as the volume rendering. You see the two neutron stars in the final few orbits before merger. They lose orbital angular momentum via gravitational wave emission until they ultimately touch, tidally deform, and then form a single object. In that, some of the material gets ejected. This is what we call the dynamical ejector. Some of that forms an accretion torus around that object. And then this, in this case, hypermassive neutron star, so a neutron star that's supported against its maximum mass if it were not spinning by differential rotation. Ultimately, as that loses differential rotation and spins down, it collapses to a black hole, which is now this black sphere in the center. So this is the overall picture. This is just a hydrodynamic simulation. But if we go away from just a single scenario, there's a couple of different outcomes that come into play. So we have the merger, and then depending on the mass of the individual neutron stars, depending on the equation of state, which is a key uncertainty in all of that, depending on the turbulent amplification, angular momentum transport, we have a couple of different outcomes. We can immediately collapse to a black hole. This is particularly for high mass mergers. We can leave a stable neutron star behind, or we can go into this intermediate phase that I've just shown you in the simulation, where we have a neutron star supported by differential or regular rotation against its maximum mass, and it collapses as this angular momentum transport redistributes this rotation. So what we have done in the group in Amsterdam was to look at this in a more parameterized way. So we started from the merger simulation that I've just shown you, but mapped the magnetic field and different magnetic fields on top to get an idea of how does that impact the merger remnant dynamics. And what you see here is basically the torus around that hypermassive neutron star that is sitting in the center. The red and gray color map here is basically unbound material. That's a magnetized wind and jet component that's driven from the magnetic field that you see the field lines here. If I play this again, you see basically how this tangled field gets organized into a tight coil that collimates some material to relatively high Lorentz factors, and you have a wind component around that. That's one particular realization starting from a strong magnetic field. It's a 10 to the 15 glass. If we vary the magnetic field, you can see from left to right, we can actually create quite different observational outcomes. So this will impact what kind of material we eject as part of the kilonova. This will impact how fast that material is moving, whether it's the blue and red kilonova. It will also impact whether we make a high Lorentz factor core in these outflows that could at least be compatible with the short GRB. Of course, there's a lot more that needs to go into modeling these to claim that they truly are GRBs. And these simulations were all basically us mapping parameterized fields on top of the remnant, resolving the turbulence for some of these, but not starting consistently from the turbulent field that you get from the merger, where you have both the Kelvin-Helmholtz instability and then the magnetorotational instability in the remnant drive the field amplification to get an idea of what's happening if we don't seed this field artificially. Ultimately, just to give you one idea of like how we connect this to observations is by actually taking the ejector from these simulations, propagating them out to like a time scale and length scale where they cool efficiently enough that we can actually look at the radioactive decay and connect this directly to kilonova light curves. So here the points are the the kilonova emission from GW 170817, and then in blue, the different light bands are here our predicted signals. And this is for a particular case of how we connect to the blue kilonova component in these simulations, but this is really just to show you that we can take these simulations and connect them to the observational signatures. But the key thing that is tricky is that there's a lot of parameters at play, and I haven't even touched the detailed turbulent evolution here yet, that we need to disentangle to really use observations like that to constrain details of the engine and details of the parameters of the merger. All of that plays into that. So this is a complicated story. So looking at the remnant and its evolution in more detail, and this is work from David Radice in 2017, doing large eddy simulations in hydrodynamics only to look at the impact of the merger evolution, the remnant evolution after the merger. So here at t equals 0, we have merger. We're looking at the maximum rest mass density in the remnant left behind, and this is for different large eddy simulations, and you see the different parameters here in terms of the mixing length. And you can see that this quite drastically can change the maximum density evolution, and ultimately all these lines that shoot up here out of the plot are ones that collapse to a black hole. So depending on what exactly is happening with angular momentum transport and details in the remnant evolution, you can determine whether you leave a neutron star behind, a black hole, or anything in between, and on what timescale this remnant collapses. So going beyond to do this in MHD, and this is again just the stability criterion for the magnetorotation instability. It's essentially the same picture as in the supernova case. You have this remnant differentially rotating. The innermost part is stabilized by entropy and composition gradients, so there's not a lot of shear happening there, but then anything outside of that delivers again magnetorotational instability. We did this similarly, trying to look at magnetic field amplification and potentially dynamo action like we did in the supernova case, but here we didn't have that much luck. So this is a 50-meter resolution for different seed fields, and we did see magnetic field amplification, but nothing that was sustained. So the fields kind of decayed again, and this is probably just lack of resolution in this particular system where the resolution requirement is a bit more stringent than in the supernova case. Recently, there's been a lot more work going beyond that. So this is work by Elias Moss and also Elliott, looking at how can we go beyond kind of compensating for not being able to fully resolve these systems in global simulations and basically dialing in small scale effects. In this case, we are a dynamo model, small scale dynamo model, and then showing that this can indeed lead to the needed field strengths to then drive these outflows that I had shown you from these simulations where we had parameterized the field and seeded it to deliver these results, that you can get them consistently if you take into account small scale dynamo action. And again, you can get kind of a diversity of outcomes from bursts to like short GRBs. And then very recently, and I think published a few weeks ago, Kenta Kiyuchi has basically done a simulation where he's consistently modeled all of this. So he's done a merger, he has put 12-meter resolution, I think, on top of that to resolve the Kelvin-Helmholtz instability, creating the seed field during the merger, and then followed about, I think, 200 milliseconds of evolution of the remnant, resolving the MRI, seeing what they call a large-scale dynamo, and seeing field created that can create these short GRB outflows consistently, not assuming any small-scale effects that are not numerically resolved in these simulations. So this is very recent. I think there's a couple of questions. Is this a robust mechanism? I think we ideally need multiple resolutions, other simulations that can confirm these results, but this looks quite promising and potentially a true breakthrough in terms of where we can get this from in neutron star merger simulations. And then just ending on a little bit of perspective. So I've shown you some examples of like what we can do in global simulations, looking at some of the turbulent evolution. But of course, we can't go to as much detail as dedicated turbulent simulations can do. We also have much more messy physics going on, since like we don't have idealized global system scales that make the analysis necessarily easy. But yet, I think that we are at a stage where we have to think about like what we can do in terms of zooming in on specific regions of interest, looking at more plasma physics that need to be included. All of these simulations were ideal MHD, so there's a lot that can mediate and change the details results of the turbulence. Think about particle acceleration and emission models in these systems to connect more easily to observations. And then ultimately include this in full-scale simulations to really connect the turbulent evolution of the engine to its observational signatures. But this is complicated, requires a lot of compute power. So are GPUs enough? I don't really know. If we can just brute forces on GPUs, we probably also need more sophisticated and more clever numerical algorithms, but also use them in an informed way where we actually think about what we're doing and where we can learn most when we explore systems like that with complicated and expensive simulations. And potentially we can use these simulations as learning tools to build models, machine learning, or in other ways to include these effects into simulations that allow us to sweep the parameter space and do more detailed sampling. So with that, let me summarize and just say that I think there's a lot of work in connecting global simulations, the turbulent evolution, learning from what has been done in dedicated turbulent simulations, and connecting all of that to the observational signatures so that we can fully maximize what we have in terms of the multi-messenger astrophysics revolution. Thank you very much.
Thank you very much, Philipp, for the exciting talk. Please, questions?
Hi, can you expand more on your definition of what's an inverse cascade?
Yeah, okay, so going back to this. In this case, it was really just that, so here I'm plotting the temporal evolution of the magnetic energy spectrum as differently colored lines. So we start, the dashed black line is our initial one. And then we first start going from red, so we first saturate here at large K, small scale, and then as time goes on, we grow this bump at K equals 4. We did also look at transfer functions and calculated those, and this K equals 4 basically corresponds to the width of the shear layer, which is kind of where we expect this large scale momentum to, the large scale energy to saturate at in terms of spatial extent, because outside of that, there's really no turbulent action. So it's really just seeing that bump grow at large K. I think there's a lot more to analyze this in detail to really get to the bottom of this. We started looking at this with transfer functions, and we did see some proof that this is not something that's completely hand wavy, but it was also complicated because you're looking at a box that doesn't have turbulence throughout. You have a hard inner boundary that is basically the surface of your proto-neutron star, which if you're calculating spectra, that makes it complicated because you basically have a hard surface there. So it was not trivial to get to the details of that. And we even went beyond and tried to build a mean field dynamo model that could kind of mimic the results of that. But at that point, it ended up being too complicated. So that's where we stopped. I think that's something to revisit that potentially can teach us a lot more about the actual physics of what we're looking at there.
Better, and then Elliot.
Very nice simulations. In the magnetary formation simulations, what is the seed magnetic field that you get 10 to 8, 10 to 9 Gauss, and what drives the amplification? The dynamo is MRI or Taylor instability or large scale shear? So can you?
Yeah, so with seed field, you mean the seed field we're starting from for the proto-neutron star that is formed in the collapse. So that is 10 to the 10 Gauss in this particular case.
10 to 10.
Yeah, which is, and this is essentially set by what we can afford numerically in terms of resolving the MRI for this particular. And the MRI is the main driver of this, the turbulence basically initiating the dynamo process. But of course, there's also large scale shear and rotation winding of field, but that's not the dominant part. It's really driven by the dynamo.
And what about Taylor instability? Because in magnetars,
yeah, we didn't see a lot of that, but we also didn't look at it in detail. So that there could be, I mean, it's a stratified medium. That of course, there could be things that are happening here that we didn't focus on in detail on that.
Thank you.
Elliot.
You alluded to other work showing that you could get magnet strength fields even without rapid rotation. Is that actually in a dipole component or just in higher order multiples?
I think from what I remember, but I don't have the details of the entire paper, I think it was in higher order multiples. I don't think they showed actual large-scale toroidal dipole field, but it was definitely basically just something that could act in the absence of rotation, which I think made it interesting. I think they faced similarly constraints in terms of how long they could evolve to actually look at potential large-scale dipole field creation.
Okay, thanks.
Andre?
So in the core collapse case, sometimes neutrino viscosity plays a big role. Was this included in any way?
It was not included. I mean, we do have neutrinos in the system, but we didn't include the viscosity. We did do a check of what would the neutrino viscosity be, shear layer, and basically it would not be a large modifying factor or not. We looked at basically MRI results in the presence of viscosity and then looked at what the neutrino viscosity would be in our particular core collapse scenario and looking at the density profile and the neutrino luminosities, and it didn't seem to apply in this case. But one thing that we did learn from that was that it is relatively fine-tuned. So depending on which particular progenitor and compactness you have and what the density profile is, it could impact some particular other situations.
Yes, so this is the infamous high magnetic Prandtl number case, which all dynamo people are referring to. So it could be interesting to look at.
Yeah.
Thank you for the question. While the audience is thinking, I will use my prerogative as a chair and ask you a question. So you get these relativistic outflows, Lorentz factors of few, which is exciting. What sets the duration of the short GRB in this picture? Would it be spin down timescale of the magnetar? Or would it be the lifetime of the hypermassive neutron star? What would you expect?
I think it really depends on what you're particularly looking at. If you do leave a stable neutron star or magnetar behind, then I think the spin down timescale there would be a natural limit at least. But if you're looking at a hypermassive neutron star, that would be much shorter, right? Like the typical lifetimes would be on the order of tens of milliseconds to potentially hundreds, but not much more. So that would be a much tougher constraint on explaining the short GRB emission that is kind of extended if you're looking at something like that. So it really depends on the remnant you leave behind. I think, whether you leave a stable neutron star behind, that's more a scenario, I think, where you need very specific conditions in terms of high mass of the neutron stars, and you need a specific equation of state to support that. So I think that's not, I would think, the most common scenario you get out of most mergers. But of course, then, you have other problems in that, right? Like that's just the intrinsic lifetime of the engine. You have then also, how do we actually make the short GRB emission from that? So then, you enter a lot more parameters into that. I think it's not that easy to fully disentangle.
Got you. Thanks. Please go ahead. One last question.
This might be a naive question, but as far as I understand, you may have a significant strong bulk viscosity from the weak force in the neutron star mergers. I'm just wondering how a strong bulk viscosity might change things like the small and large scale dynamo, if you've thought about this at all.
I have not really thought about this. We are thinking to extend to look at including bulk viscosity and neutron star mergers, and tying that into a larger multi-messenger framework to constrain nuclear physics and details of heavy ion collisions and things that play a role here. But I've not thought particularly about how that would change the turbulent evolution and potential dynamo action. I think that's something that would be potentially really interesting to look at.
Wonderful. Thank you so much for the questions. Let's thank the speaker once again.